Hey, welcome. Today we're diving deep, literally, into the very foundation of our world. We are talking about minerals and rocks. You know, the hidden architects behind everything, from the mountains outside your window to the microchips in your pocket.
But first, let's start with a little puzzle. Think about the phone you're probably holding, the salt in your kitchen, and a massive skyscraper downtown. What on earth could those three things possibly have in common? They seem like they're from completely different worlds, right? But they're not.
Well, here's the answer. Every single one of them started its journey inside the Earth. The silicon in your phone's chips, that comes from a mineral called quartz. The salt on your fries, that's actually the mineral halite. And those huge skyscrapers, they're basically held together with cement made from limestone. So the real question is, how do we get from a simple stone to our complex world? Let's dig in.
To really get a grip on all this geology stuff, we've got to start small. Before we can even begin to talk about massive mountains and canyons, we need to meet their basic fundamental ingredients, minerals.
So what is a mineral, really? It's not just some random rock you pick up. Oh no, geologists are super specific about this. To earn the title mineral, a substance has to check off 5 boxes on a very strict list. It's an all-or-nothing kind of deal.
Okay, here are the 5 rules. First, it's got to be a solid. No liquids, no gases. Second, it has to be found in nature. So a lab-grown diamond, technically not a mineral. Third, it has to be inorganic, which just means it wasn't made by a living thing, like a plant or an animal. Fourth, it has a specific chemical recipe. Quartz is always SiO2, period. And finally, and this is a big one, its atoms are arranged in a super neat repeating pattern. We call that a crystalline structure.
And that brings us to the most important difference to remember. A mineral is like one pure ingredient. A rock, on the other hand, is the finished product. It's a mixture of those ingredients. So think of it like this. Minerals are your flour, your sugar, your chocolate chips. A rock, that's the delicious cookie you bake with all of them.
Now, one of the coolest ways geologists can tell minerals apart is just by looking at how they shine, or what they call luster. And it's way more than just shiny or dull. You've got the crazy fiery sparkle of a diamond, which they call adamantine. Then there's the glassy shine of quartz, which is called vitreous. You can even have silky, greasy, or earthy lusters. Each one is like a little clue to the mineral's true identity.
All right, so we have our basic ingredients, the minerals. Now let's see what happens when they get together. They form 3 major rock families. And believe me, each one has a completely different and pretty epic origin story.
First up, you've got igneous rocks, literally born from fire. They're what you get when molten hot magma or lava cools down and hardens. Then you have sedimentary rocks. These are like the Earth's scrapbooks, formed from layers of sand, shells, and little bits of other rocks all getting squished together over millions of years. And finally, you have metamorphic rocks. These are the transformers of the rock world. They start as one type of rock and then get totally changed by incredible heat and pressure deep inside the Earth.
So how can we look at a rock and know which family it belongs to? Well, the biggest giveaway is its texture. And I don't just mean how it feels in your hand. We're talking about the size, shape, and pattern of its mineral bits. It's kind of like reading a page from the rock's own autobiography.
For igneous rocks, the whole story comes down to one thing: cooling speed. If magma cools down super slowly, miles under the ground, we call it a plutonic rock. But if it shoots out of a volcano as lava and cools almost instantly, it's a volcanic rock. And you can actually see the result of that cooling speed. It's amazing. Slow cooling gives the minerals tons of time to grow into big, chunky crystals that you can easily see. That gives it a phaneritic texture. Think of a granite countertop. But when the lava cools super fast, it freezes the crystals when they're still tiny, creating a fine-grained aphanetic texture, like you see in that dark volcanic rock, basalt. The other rock families have their own stories to tell too. A sedimentary rock might show you little bits of older rocks all glued together, or maybe crystals that were left behind when water evaporated, or even tiny fossils from ancient sea creatures. And metamorphic rocks? Under immense pressure, their minerals can line up in these beautiful layers and bands. Geologists call that foliation. Or if the pressure was even on all sides, they might have more of a uniform, sugary look.
So it's pretty clear we can figure out a rock's entire life story just from its texture. But why does this all matter? Okay, let's bring it back from the ancient past to right now and see how these stones literally build our modern lives.
The world as we know it is built from this stuff. I mean, it's everywhere. Limestone and gypsum give us our walls and homes. Granite and marble make our buildings look incredible. Quartz is the tiny engine inside our computers and watches. Graphite is in your pencil. Halite is on your table. And rocks like coal and uranite are powering this entire civilization. It's mind-blowing when you think about it.
So the bottom line is that every single stone tells a story. And once you understand the difference between a mineral and a rock, the 3 rock families, and the clues hidden in their textures, you've basically learned a whole new language. You can look at a countertop, a curbstone, or a mountain range and start to read the deep, incredible history of our planet, a history that's written, quite literally, in stone.